The jets of high-energy particles and associated electromagnetic funnels produced by spinning supermassive black holes are immensely powerful, affecting the evolution of galaxies and even clusters of galaxies that span millions of light years. All this energy is from a powerhouse roughly the size of our solar system. Proportionately, it is as if an energy source the size of a blueberry could heat a gas cloud the size of Earth to millions of degrees Celsius. It seems mind-boggling, but many astrophysicists now concur that the power from rotating supermassive black holes can be used to solve a long-standing puzzle called the cooling flow problem. Recall that the hot gas in galaxy clusters contains more mass than all the stars in all the hundreds, and in some cases thousands, of galaxies in a cluster. The gas, which is heated primarily by the slow gravitational collapse of the cluster, has a temperature of tens of millions of degrees and glows brightly in X-rays. Optical telescopes cannot see it, and X-rays cannot penetrate Earth's atmosphere, so the discovery and study of this gas has depended on orbiting observatories. 2 decades ago, astronomers observing with NASA's Einstein X-ray Observatory and other instruments noticed that the X-rays carry away so much energy that the gas should cool off and settle into the center of the cluster, thus the term cooling flow. Andrew Fabian and his colleagues led the way in investigating these flows with Einstein and the follow-up ROSAT X-ray satellite. They showed that if the flows persisted for 1 billion years, the gas deposited in the central regions of the cluster could form trillions of new stars. The only trouble was, no one could find these stars. Observers looked in vain for large amounts of cool gas and hordes of newly formed stars. If a black hole had swallowed them all, it would weigh as much as 1 trillion stars, and not even the biggest black hole is that massive. Some astrophysicists maintained that, in this case, the absence of evidence was evidence of absence, and that large-scale, long-term cooling flows do not exist. A possible explanation was that the central galaxy of the cluster somehow produces energetic outflows that heat the gas enough to offset the radiative cooling. Radio astronomers had for years been accumulating evidence for such outflows, yet it was uncertain whether the outflows could provide enough energy distributed over a large enough volume to halt the cooling flows. Resolving the cooling flow problem was one of the goals of both Chandra and XMM Newton. Because the gas radiates away its energy fairly slowly, it preserves a record of the past activity in the clusters over the last few billion years. For instance, it retains the elements and energy injected into it by supernova explosions in the cluster galaxies. Like archaeologists unearthing the past, astronomers have used the new telescopes to excavate the relics present in galaxy clusters and piece together their histories. The brightest cluster in X-rays is the Perseus cluster. It has a high intrinsic luminosity and, at a distance of about 250 million light-years, is relatively nearby. In the 1990s, ROSAT discovered 2 vast holes in the X-ray emission in the central 50,000 light-years of the cluster around the giant galaxy NGC 1275. With Chandra, Fabian and his colleagues went back for a closer look. The Chandra image showed the cavities in exquisite detail. When the radio data were added to the Chandra image, the jets fit nicely inside the cavities. The X-ray cavities are almost empty of hot gas, but they are not altogether empty. They are filled with high-energy protons and electrons and magnetic fields. These bubbles have a lower density than the hot gas, so they rise buoyantly, like bubbles in boiling water, and push aside the hot gas. By special processing of the Perseus cluster images, Fabian's team unveiled a series of nearly concentric ripples. The density and pressure of the gas, though not its temperature, change abruptly at the innermost ripple, indicating that this feature is a weak shock wave. At the outer ripples, the density and pressure vary gradually, indicating that these ripples are sound waves. The spacing of the ripples, 35,000 light-years, and the calculated speed of sound in the gas under these conditions, 2.6 million miles per hour, imply that 10 million years passed between the events producing the ripples. The pitch of the sound waves translates to a note of B flat, 57 octaves below middle C on a piano. In the Virgo galaxy cluster, the nearest cluster to us at a distance of about 50 million light-years, William Foreman of Harvard-Smithsonian and his colleagues observed the central dominant galaxy in this cluster, M87, using Chandra. In addition to the jet from the black hole, they found a web of filamentary structures farther out, each about 1,000 light-years across and 50,000 light-years long. The filaments may be formed from a series of buoyant bubbles arising from outbursts spaced about 6 million years apart. Foreman's team also detected a ring of hotter emission with a radius of about 40,000 light-years, probably a weak shock front, as well as a large X-ray cavity about 70,000 light-years from the galaxy's center. The sound waves in this case might be about an octave higher in pitch than those of the Perseus black hole. Similar features show up in other clusters and in groups of galaxies as well. Groups are smaller versions of their cosmic cousins, galaxy clusters. Instead of containing thousands of galaxies, as clusters do, they typically have a handful of large galaxies and a few dozen dwarf galaxies. Many, but not all, groups also contain huge clouds of multi-million-degree gas. The galaxy NGC 5813 is part of a group about 100 million light-years from Earth. The group contains another large galaxy, NGC 5846, and more than 200 smaller galaxies clustered around the two larger galaxies. Chandra observations of the region around the NGC 5813 subgroup reveal evidence that multiple eruptions have occurred in this group over the course of the past 50 million years. 3 pairs of collinear cavities with bright rims of X-ray emission were detected at 3,000, 25,000, and 64,000 light-years from the central supermassive black hole, which has a mass of 280 million solar masses. The cavities all had bright rims characteristic of shock waves moving through the hot gas at about Mach 1.5, or 1.5 times the speed of sound. The shock speeds, together with the size of the cavities, imply that distinct outbursts occurred about 2 million, 15 million, and 50 million years ago. The shock energy appears to be sufficient to balance the radiative cooling of the hot gas. Chandra observations by Brian McNamara of the University of Waterloo in Canada and his colleagues revealed X-ray cavities with associated radio emission in the Hydra A, Hercules A, and Abell 2597 clusters. They also discovered bubbles that were faint in both radio waves and X-rays, indicating that the energetic particles in them have dissipated most of their energy. These ghost cavities are displaced well away from the central black hole and may be relics of past activity. McNamara and colleagues also used Chandra to discover the most spectacular cavities yet. They are in the cluster MS 0735.6 plus 7421. Although the image is not as detailed as the one of Perseus, it tells an amazing story. Each of the 2 opposing X-ray cavities is about 640,000 light-years across, nearly 7 times larger than the disk of our Milky Way galaxy. The size of the cavities and the observed density and temperature of the gas around them indicates they are 100 million years old and contain as much kinetic energy as 10 billion supernovas. John Peterson of Purdue University and his colleagues used XMM Newton to make a comprehensive study of clusters with and without cooling flows. Their research shows that cooling flows do not occur in clusters that have such high-energy bubbles. Somehow, the bubbles are transferring heat to the gas and preventing it from cooling. Exactly how they are doing this is still an open question. Various proposals, shock waves, heat conduction from the hot outer gas, heating by the high-energy particles in the bubbles, or the decay of turbulent eddies, have been floated, but no one mechanism has gained acceptance. But the biggest question of all, namely where the energy came from to begin with, has been answered. A rapidly spinning supermassive black hole can do it. Calculations show that black hole jets have two major components: a matter-dominated outflow that moves at about a third of the speed of light, forming the outer sheath of the funnel, and an inner region along the axis of the funnel that contains a rarefied gas of extremely high-energy particles. It is the inner region that carries much of the energy and creates the dramatic structures observed in Perseus and other galaxy clusters. One of the most astounding features of jets is the pencil-thin shape that they can maintain despite traveling hundreds of thousands of light-years, far beyond the confines of their parent galaxies. The pressure of the gas near the black hole can get a jet started as a narrow beam, and it may be that inertia keeps the jet narrow, much like a blast of water from a hose or steam from a high-pressure tea kettle. The tightly coiled magnetic field that is spun out with the jet may also play a role. Regardless of the confining mechanism, the pressure of the rarefied gas through which jets move gradually takes its toll. The jets slow down and billow out, creating enormous magnetized clouds of high-energy particles. These clouds continue to expand, pushing out the surrounding gas to create the dark X-ray cavities observed by Chandra. This sequence of events, gas falls into a rapidly spinning black hole to form megajets that carve out gigantic bubbles of high-energy particles and heat vast volumes of space, is feedback of truly cosmic proportions. The black hole is both responding to and influencing events on the scale of the entire galaxy cluster. A likely scenario is as follows. Initially, the gas in the cluster is very hot, and the supermassive black hole in a centrally located large galaxy is quiet. Over about 100 million years, gas in the central region of the cluster cools and drifts toward the central galaxy in a cooling flow where it can form stars. Some of the gas in this cooling flow condenses into stars that become part of the central galaxy, and some sinks farther inward to feed the supermassive black hole. In so doing, it creates an accretion disk and activates high-powered jets. The jets blast through the galaxy and out into the cluster gas, where they heat the gas. The cooling flow is greatly diminished, if not shut off altogether. The supply of gas to the supermassive black hole declines. Without an abundant gas supply, the supermassive black hole gradually becomes dormant and the jets fade away, leaving the cluster gas without a heat source. Millions of years later, the hot gas in the central region of the cluster cools sufficiently to initiate a new season of growth for the galaxy and its supermassive black hole, and thus the cycle continues. This scenario is supported by high-resolution X-ray and radio images of the NGC 5813 group, as well as Virgo, Perseus, Hydra, and other clusters, which show evidence of repetitive outbursts from the vicinity of the central galaxy's supermassive black holes. Magnetized rings, bubbles, plumes, and jets, ranging in size from a few thousand to a few 100,000 light-years, strongly suggest that intermittent violent activity has been ongoing in these clusters for hundreds of millions of years. One of the most spectacular examples of the star formation part of the process is the brightest galaxy in the Phoenix cluster, which is seen at a look-back time of 5.7 billion years. This system has the mass of about 500 billion suns, and it produces more X-rays than any other known cluster. Over the past few million years, stars have been forming in this galaxy at the astounding rate of 600 solar masses per year, compared to a rate of perhaps 1 per year for the Milky Way galaxy. Chandra data also reveal the presence of deep X-ray cavities in the inner 30,000 light-years of the 50 million degrees Celsius gas cloud that envelops the central region of the cluster, an indication that the cycle of infall, blowback, cooling, and so forth has been ongoing for some time. One startling implication is that the supermassive black holes in the centers of these clusters are still growing at a rapid rate even to the present day. Astrophysicists had thought that the growth of supermassive black holes had tapered off a few billion years ago. In the case of cluster MS-0735, the activity indicates that the supermassive black hole has gulped down the equivalent of 300 million suns in the past 100 million years, nearly doubling in size and mass over that relatively brief interval. Yet, the central black hole shows no other signs of activity, such as bright X-rays or visible light, which are usually emitted by active holes. It is only through the X-ray cavities that we can discern the properties of this amazing system. Galaxy collisions, an ever-present hazard in the central regions of galaxy clusters, can rekindle a supermassive black hole's activity by giving it another generous serving of matter. A smaller galaxy passing too close to the giant central galaxy is torn asunder. Its stars are assimilated. Some of its gas goes down the black hole drain, and its own central black hole merges with the one in the giant galaxy. The enormous cavities observed in MS-0735 were probably the end result of a sequence of events initiated when a merging galaxy caused a huge influx of gas into a supermassive black hole. The role of collisions may help scientists to understand the evolution of galaxies in the early universe, when galaxies were closer together and mergers of galaxies were common. A growing body of research indicates that many aspects of galaxy formation and evolution, the size of galaxies, the shapes of galaxies, the rate of star formation, can be understood in terms of a cosmic cycle involving mergers of galaxies. Large-scale computer simulations by Philip Hopkins of Caltech and his colleagues show that mergers of gas-rich galaxies trigger bursts of star formation and inflow of gas into the central region. The inflowing gas fuels rapid growth of the supermassive black hole and intense radiation from its vicinity. Blowback ejects much of the gas from the galaxy. Star formation rapidly slows, and accretion onto the black hole declines until another merger occurs. Most of the black hole feedback that shaped the evolution of galaxies occurred about 8 to 10 billion years ago when they were young. This epoch can be observed only in distant galaxies, which makes the study of details such as jets, bubbles, and waves difficult. Fortunately, similar, though not identical, blowback processes are occurring in relatively nearby galaxy clusters where Chandra can directly image and measure them. It may seem strange that supermassive black holes, objects with masses that range from a few million to hundreds of millions of solar masses, can have such a large impact on galaxies whose masses range from a few billion to a few hundred billion solar masses, let alone galaxy clusters with masses measured in the hundreds of trillions of solar masses. The reason is the concentrated nature of supermassive black holes and their gravitational fields. Supermassive black holes are by far the largest supply of gravitational potential energy in an entire galaxy. By tapping this energy through accretion disks and the launching of powerful megajets, black hole feedback is one of the most important processes at work in the universe. So maybe black holes aren't all bad. In fact, maybe bad is the new good, as the song goes. In centuries past, there was a belief that the stars governed our fate through cosmic sympathy. Occurrences in the macrocosm, or the heavens, were thought to presage fateful events in the microcosm, such as success or failure in battle or the death of a powerful ruler. For this reason, court astrologers took their work seriously, and, well, they should have. Their lives literally depended on it. They could be executed for failure to predict an eclipse. Today's astronomers are beneficiaries of the meticulous record-keeping of ancient Chinese, Japanese, Korean, Arabic, and European observers. An excerpt from the Chronicles of the Sung Dynasty contains an account of the observation of the supernova of 1054 CE that produced the Crab Nebula. This account hints at the flavor of the times and the conditions under which the court astrologers worked. Prostrating myself, I have observed the appearance of a guest star. On the star there was a slightly iridescent yellow color. Respectfully, according to the dispositions of the emperor, I have prognosticated, and the result said, "The guest star does not infringe on Aldebaran. This shows that the plentiful one is Lord and that the country has a great worth." Duivendak, 1942. If you take into account the passage of 10 centuries and the developments in science and technology since then, this report could pass for a progress report on a research grant from the National Science Foundation, or NASA. Interdisciplinary research on the reports of astrologers by historians and astronomers provides a valuable record of the most violent events that have occurred in our galaxy over the past 2 millennia. Current estimates suggest that about 36 supernovas should have occurred in the galaxy over that time. The relative scarcity of reported supernovas may be due to several factors. Many of the events could have been in the southern sky, others could have occurred on the far side of the galaxy, and some might have been embedded in obscuring clouds of dust and gas. The records contain many reports of new stars, guest stars, and stellar novae, but only a few of them were supernovas. The supernovas are distinguished by 2 criteria. 1, the duration of time over which they could be observed, at least 3 months and as long as 3 years in the case of the supernova of 1006 CE, and 2, by the discovery in modern times of expanding supernova remnants of hot gas and energetic particles at the locations of the reported supernovas. The brightest supernova observed was the supernova of 1006 CE, which was brighter than Venus and visible for several years. However, the remnant of SN 1006 has not attracted nearly as much attention as the supernova of 1054 CE. This is because SN 1006 was likely produced by a thermonuclear explosion that completely disintegrated a white dwarf star, a type Ia explosion, and left nothing behind except the expanding stellar debris. In contrast, the Crab Nebula was the product of the collapse of the core of a massive star. The collapse triggered a supernova that ejected most of the star, but left behind a rapidly spinning neutron star. This cosmic dynamo produces a tornado of magnetic fields and high-energy particles that continue to light up the expanding debris. The detection by Chandra of rapidly spinning neutron stars and supernova remnants is proving to be one of the best ways to distinguish between the types of supernova explosions, and thereby to understand the nature of the star that exploded. All the historical supernovas occurred thousands of light years away, so their physical effects on Earth were negligible. However, one supernova played an important role in the development of modern physics and astronomy. The supernova of 1572 occurred before the invention of the telescope, before Galileo and Newton, at a time when the concept of an exploding star was less plausible than witchcraft. An exploding star was contrary to the order of nature, according to which stars were symbols of the eternal and unchangeable, part of a realm of permanence located above the ever-changing, ever-corruptible world below. Then, in November 1572, a star brighter than the planet Venus appeared suddenly in the constellation of Cassiopeia. Make no mistake, these people did not know calculus because it hadn't been invented yet, and they had some strange ideas about what happened on Halloween, but they knew the sky far better than most of us. The new star, or nova, to use the Latin of 1572, was noticed throughout Europe and in Asia. The appearance of the nova of 1572 and the subsequent detailed description of its properties by Tycho Brahe played a major role in revolutionizing astronomy and all of science. Tycho, as he was known, was a stormy, boisterous astronomer known for his acid tongue and brass nose. Where he got the acid tongue is a matter of speculation. What is known about his childhood suggests it could have been a result of either heredity or environment, or both. The brass nose, it is sometimes reported that Tycho's nose was silver, but in 2010 his body was exhumed to confirm that it was not, is another matter. It was acquired when Tycho lost his natural nose in a duel at age 20, reportedly precipitated by an argument with a fellow student over who was the best mathematician. Tycho, as it turns out, was neither a particularly good mathematician nor a skilled swordsman, but he was a great astronomer, probably the greatest of the age before the telescope. He built elaborate instruments for locating stars on the celestial sphere, kept meticulous records, and worked diligently. He noticed the nova of 1572 right away, and he immediately set to work making accurate measurements of its position in the sky relative to other stars in the constellation of Cassiopeia, where the star appeared. He showed that, although the brightness of the star declined steadily from being as bright as Venus until it became invisible, its position remained fixed. This proved that the new star was not a comet. It belonged to the eighth sphere of the fixed stars. The explosion of the star had shattered forever the widely accepted doctrine of the incorruptibility of the stars, and it set the stage for the work of Kepler, Galileo, Newton, and other eminent scientists of the time. Fast forward to 1934, when Fritz Zwicky and Walter Baade presented evidence for a previously unrecognized celestial phenomenon, which they called a supernova. Other stellar outbursts called novae were well known by then, and their properties fairly well described. In fact, Hubble had used the characteristics of novas to show that the Andromeda and other galaxies are millions of light years from Earth and are vast assemblages of stars like the Milky Way galaxy. Zwicky and Baade argued that supernovas are millions of times more energetic than ordinary novas, and each clearly represents an explosive event that involves an entire star, not just its outer layers. They and their colleagues undertook comprehensive surveys to search for supernovas. By the time the decade was out, their existence as a new type of phenomenon was well established, and Tycho's nova was upgraded as Tycho's supernova a few years later. In 1941, Rudolf Minkowski showed that supernovas could be divided into two types based on their optical properties. Type 1 explosions do not show evidence for hydrogen in the expanding debris ejected in the explosion, but Type 2 supernovas do show such evidence. As other astronomers joined in the hunt for supernovas and the number of discovered supernovas increased exponentially, it became evident that Type 2 supernovas occurred in regions with lots of bright young stars, such as the spiral arms of galaxies. They apparently do not occur in elliptical galaxies, which are dominated by old low-mass stars. Since bright young stars are typically stars with masses greater than about 10 times the mass of the Sun, this and other evidence led to the conclusion that Type 2 supernovas are produced by massive stars. Type 1 supernovas were soon divided into subclasses 1A, 1B, and 1C. Types 1B and 1C turned out to be more like Type 2 supernovas, but Type 1A supernovas were different. Unlike the other types of supernovas, Type 1A supernovas generally occur in all types of galaxies, including ellipticals, and they show no preference for regions of current stellar formation. This means that they likely come from an older stellar population. Finally, the variation of the light from Type 1A supernovas with time, called the light curve, was very similar for all Type 1A events and markedly different from the other types. In 1945, Baade, in a remarkable bit of forensic astronomy, used Tycho's description of the supernova of 1572 to show that it fits nicely into the Type 1A category. A hunt for the supernova remnant proved fruitless until radio astronomers at Jodrell Bank in England found a strong source of radio waves near the position of Tycho's supernova. In the 1960s, the remnant of Tycho's supernova was finally detected as a faint nebula. In 1970, Paul Gorenstein of the Harvard-Smithsonian Center for Astrophysics and his colleagues discovered X-ray emission from Tycho's supernova remnant by using an X-ray detector aboard a sounding rocket. In 2008, Oliver Krauss of the Max Planck Institute analyzed light echoes produced from the scattering of light off interstellar clouds near Tycho to view the supernova 436 years after the event, and confirmed that Tycho's supernova was indeed a Type 1a supernova. In 1973, John Whalen and Iko Eben Jr. of the University of Illinois proposed that a Type 1a supernova is produced by the explosion of a white dwarf star. As the condensed remnant of what used to be a sun-like star, a white dwarf star is a dense ball primarily composed of carbon and oxygen atoms. It is intrinsically the most stable of stars, as long as its mass remains below the so-called Chandrasekhar limit of 1.4 solar masses. White dwarfs are among the dimmest stars in the universe. Even so, they have commanded the attention of astronomers ever since the first white dwarf was discovered in the middle of the 19th century. One reason for this interest is that white dwarfs represent an intriguing state of matter. Another reason is that most stars, including our Sun, will become white dwarfs when they reach their final, burned-out, collapsed state. For time out of mind, Sirius, the brightest star in the sky, has played a prominent and sometimes peculiar role in mythology and astronomy. In ancient Egypt, Sirius's hieroglyph, the dog, appeared on monuments and temple walls dating back beyond 3000 BCE. The rising of Sirius just before the sun on the summer solstice signaled the beginning of summer, and coincidentally the coming flooding of the Nile, an event critical for supplying the water necessary for agriculture. The temple of Isis Hathor at Dendera and numerous other temples in the Nile Valley were oriented to the rising of Sirius. In ancient Greece and Rome, Sirius was thought to be a bad influence, responsible for drought, disease, and madness in dogs. We still speak of the dog days of summer in reference to the ancient association of Sirius with the withering heat of July and August. The brightness of Sirius led the celebrated philosopher and cosmologist Immanuel Kant to speculate in the 18th century that Sirius is the center of our Milky Way galaxy, an intriguing but wrong idea. Sirius appears so bright because it is very near to Earth, at a distance of 8.7 light-years, and because it is intrinsically more luminous than an average star. Sirius was in the news, at least among astronomers, in the 1830s and 1840s, when the astronomer and mathematician Frederick Bessel concluded that the apparent motion of Sirius was not a smooth arc, but an irregular curved path caused by an invisible companion. The theoretical orbit of this companion was computed, but a search for the companion to Sirius was fruitless. Then, in 1862, Alvin Clark, a renowned telescope maker, wanted to test out his latest creation, an 18.5-inch refracting telescope at the Dearborn Observatory of Northwestern University. He decided to check it out on Sirius, and he quickly discovered the dark companion to the dog star. Subsequent studies of the companion, which was called Sirius B, or the Pup, led to the conclusion that it was hotter than the Sun, with a diameter less than 1% of that of the Sun. When they were first discovered, white dwarfs presented a paradox to astronomers. If a white dwarf couldn't produce energy through nuclear fusion, how could it generate the pressure necessary to keep it from collapsing further? It didn't seem possible, yet there they were, glowing dimly and reminding scientists that the fault is not in the stars but in their theories, to paraphrase Shakespeare. An explanation would have to await the development of the quantum theory of matter half a century later. A star is born when a cloud of gas and dust collapses to the point where the material in the center of the clump is so dense and hot that the nuclear fusion of hydrogen nuclei into helium nuclei can occur. The outflow of energy released by these reactions provides the pressure necessary to halt the collapse. The nuclear reactions inside stars are nuclear fusion reactions, in which the nuclei of light elements are fused together to form heavier elements. For example, Hydrogen nuclei are combined to form a helium nucleus, with the release of energy. In contrast, nuclear power plants on Earth produce energy through nuclear fission, in which the nuclei of heavier elements such as uranium split apart to form smaller nuclei with the release of energy. Fusion of hydrogen into helium in the core of a star can sustain a star like the Sun for billions of years. The Sun is now in this long-lived phase of its evolution, called the main sequence phase. A star experiences an energy crisis, and its core collapses when the star's basic non-renewable energy source, hydrogen, is used up. A shell of hydrogen on the edge of the collapsed core will be compressed and heated. The nuclear fusion of the hydrogen in the shell will produce a new surge of power that will cause the outer layers of the star to expand until it has a diameter 100 times its present value. This is called the red giant phase of a star's existence. 100 million years after the red giant phase, all of the star's available energy resources will be used up. The exhausted red giant will puff off its outer layer, leaving behind a hot core. This hot core is called a Wolf-Rayet type star, after the astronomers who first identified these objects. This star has a surface temperature of about 50,000 degrees Celsius and is rapidly boiling off its outer layers in a fast wind, traveling 3.7 million miles per hour. The radiation from the hot star heats the slowly moving red giant atmosphere and creates a complex and graceful filamentary shell called a planetary nebula, so called because it looks like the disk of a planet when viewed with a small telescope. X-ray images reveal clouds of multi-million degree Celsius gas that have been compressed and heated by the fast stellar wind. Eventually, the central star will collapse to form a white dwarf star. In the white dwarf state, all the material contained in the star, minus the amount blown off in the red giant phase, will be packed into a volume 1/millionth the size of the original star. An object the size of an olive made of this material would have the same mass as an automobile. For 1 billion or so years after a star collapses to form a white dwarf, it is white hot, with surface temperatures of about 20,000 degrees Celsius. It is at this point that degenerate electron pressure kicks in to support the star. Quantum theory shows that matter in so-called degenerate states of extremely high density can produce a type of pressure called electron degeneracy pressure. This is because, according to one of the fundamental principles of the theory, no more than one electron can occupy the same energy state. To see how this works, think about a parking tower connected to a shopping mall. Only one car is allowed per space. When business is slow, the parking lot is nearly empty and there is very little movement among the cars. From time to time, a car will enter and park on the lower level and one will leave. As the holiday season approaches, however, the situation changes. The parking lot begins to fill up and spaces are harder to come by. Drivers race from one level to the next, searching for an empty space. The pressure builds to get into position whenever a space opens up. The extremely dense matter of a white dwarf is like a parking lot in a shopping mall on the last weekend before Christmas. All of the low energy levels are degenerate or filled, so the electrons are forced into higher energy states, not because they are being supplied with energy from another source, but because there is nowhere else to go. This creates a degenerate electron pressure. Degenerate refers here not to the moral character of the electrons, but to the fact that all the low-energy states are occupied. This pressure is what prevents white dwarf stars from collapsing under their own weight. In 1926, Ralph Fowler of Cambridge University, using the new theory of quantum mechanics, proposed that white dwarf stars are supported by degenerate electron pressure, a peculiar property of very dense material. A few years later, one of Fowler's research students, Subramanian Chandrasekhar, known to his friends and colleagues as Chandra, worked out the theory in detail. In 1999, NASA named the Chandra X-ray Observatory in his honor. Chandra used Einstein's relativity theory and quantum mechanics to show that degenerate electron pressure can do only so much. If the mass of the white dwarf becomes greater than about 1.4 times the mass of the Sun, called the Chandrasekhar limit, it will collapse to become a neutron star or black hole, or it will blow itself apart in a supernova. This discovery created a big stir, since it showed that the theories of quantum mechanics and relativity could help explain cosmic mysteries. But not everyone agreed. One of the skeptics was Arthur Eddington, a towering figure in astrophysics. He had led one of the solar eclipse expeditions that confirmed Einstein's general theory of relativity, and he had written a prescient book on stellar evolution, in which he anticipated that the newly developed quantum theory would solve the question as to how stars burned. Eddington had also befriended Chandra, who as a young scientist had emigrated to England from India. But he thought that Chandra was wrong about the implication that massive stars were doomed to collapse. "I think there should be a law of nature to prevent a star from behaving in this absurd way," he protested. The controversy stewed for several years and ended the friendship, but in the end everyone who studied Chandra's work, everyone but Eddington that is, agreed that Eddington was wrong and Chandra was right. In the normal course of evolution, a white dwarf just cools down over the course of billions of years to become an inert stellar cinder. If, however, a white dwarf is a member of a binary system, and accretion of matter from a companion star pushes a white dwarf star over the Chandrasekhar limit, it becomes unstable, heats up, and explodes like a thermonuclear bomb, leaving nothing behind. The expanding cloud of ejecta glows brightly for many weeks as radioactive nickel produced in the explosion decays into cobalt and then iron. A Type 1a supernova occurs every 200 years or so in a galaxy the size of our Milky Way. The supernova is extremely bright, with an optical luminosity of several billion suns for a few months. The expanding stellar ejecta disperse heavy elements that enrich the interstellar gas and create cosmic sonic booms, or shock waves, that heat the interstellar gas, accelerate particles to extremely high energies, and trigger the formation of new stars. Interstellar matter is swept up by the supernova shock wave, often called the forward shock wave, into a thin shell. This material, which is mostly in the form of hydrogen gas, with a few impurities of heavier elements and dust grains, is heated to temperatures of millions of degrees and broken down into a mix of protons and electrons. The shock wave also accelerates some of the electrons and protons to extremely high energies. Electrons spiraling around the magnetic field behind the shock wave produce radiation, called synchrotron radiation because it was first observed in synchrotron particle accelerators on Earth, over a wide range of wavelengths from radio waves to X-rays. Radio astronomers detected radiosynchrotron radiation when they discovered the remnants of Tychos and other supernovas. As the supernova expands, the shell of hot, swept-up interstellar matter exerts a back pressure on the expanding stellar ejecta. This back pressure drives what is called a reverse shock wave back into the stellar ejecta. We encounter reverse waves, hopefully not shock waves, frequently when driving in rush hour traffic on the highway. A vehicle far ahead of us may slam on the brakes to avoid a road hazard. The next vehicle in the lane will brake to avoid a collision, and so on, sending a wave of braking and brake lights moving back down the lane. In a similar way, the reverse shock wave sweeps through the stellar ejecta and heats it up to millions of degrees. With Chandra, it has become possible to observe both the shock wave and the ejecta heated by the reverse shock wave. The Chandra image of the Tycho supernova remnant reveals fascinating details of the turbulent debris created by the supernova. The forward shock wave produced by the expanding debris is outlined by strikingly sharp blue circular arcs on the outer rim. The stellar debris, which has a temperature of about 10 million degrees and is visible only in X-rays, shows up as mottled yellow, green, and red turbulent clumps of gas. No central point source is detected. The absence of such a source is consistent with other evidence that Tycho's supernova signaled the detonation and destruction of a white dwarf star. Hardly anyone argues with this conclusion. Exactly how the white dwarf explodes in a Type 1a supernova, though, has been the subject of wild swings of opinion. Is a Type 1a supernova caused by a death spiral of two white dwarfs that merge and then explode, the double degenerate model? Or is the explosion caused by a white dwarf that accretes so much matter from a red giant companion star that it is pushed over the Chandrasekhar limit, the single degenerate model? Both scenarios have been around for more than 3 decades, and both have gone in and out of favor. In a 2001 review, the double degenerate model was all but consigned to the trash heap of failed models. But by 2012, the situation had been reversed, partly due to improved theoretical modeling of the explosion process, and it was cited as the most promising model. Tycho's supernova is a poster child for this puzzle, with some research papers saying that researchers have found evidence for the surviving companion star of the supernova, whereas others report that they have done exhaustive searches and come up empty. The specific characteristics of the progenitor binary system are expected to have an important imprint on the circumstellar medium into which the supernova shock ejecta expand. In particular, if one of the companion stars is a red giant, the wind usually associated with a red giant would modify the environment of the pre-supernova system by creating a low-density cavity bounded by a shell of gas. This modification would have detectable effects on the evolution of the shock wave, which should be detectable in the shape of the supernova remnants and their spectra. Chandra observations of a sample of 7 Type 1a supernova remnants show no evidence for a fast wind, contrary to expectations for some single degenerate models. Then there is the remnant of the supernova named after Johannes Kepler, which does show evidence of a fast wind. Kepler was not the first to observe the supernova, but he made it his by observing it continually for a year, beginning shortly after it had appeared, and followed this up with the publication of a book describing his observations in great detail. The Chandra image of the Kepler supernova remnant reveals a rapidly expanding nebula that shares features with the image of Tycho's supernova remnant, a thin blue shell defining the high-energy electrons produced by the supernova shockwave, and the turbulent interior of the shocked stellar debris. However, Kepler's supernova remnant shows more structure than the chaotic interior of Tycho's supernova remnant. The bright northern rim of Kepler's supernova remnant has been interpreted as an enhancement caused by the shockwave running into material ejected before the supernova by a red giant companion to the white dwarf star. In addition, a disc-shaped structure near the center of the remnant is apparent, and it provides 2 more pieces of evidence for a giant companion star: an enhanced amount of magnesium, an element not produced in Type 1a supernovas in any great abundance, and bright infrared emission, also indicative of a pre-existing dusty circumstellar disk. Theoretical simulations seeking to reproduce the outer rim indicate that the progenitor was a binary star system consisting of a white dwarf and a giant companion star of 4 to 5 solar masses. In this case, the white dwarf exploded only about 100 million years after it had formed. If such prompt supernovas occur, they could have implications far beyond the galaxy. Because Type 1a supernovas all occur in stars that have a mass of about 1.4 solar masses, they produce about the same amount of light and have a characteristic light curve. As discussed earlier, this property makes them extremely useful as distance indicators. If one Type 1a supernova is dimmer than another, it must be farther away by an amount that can be calculated. In recent years, Type 1a supernovas have been used to determine the rate of expansion of the universe. This research has led to the discovery that the universe's expansion is accelerating, possibly because it is filled with a mysterious substance called dark energy. One constraint on this method is that it takes time, roughly 1 billion years, for an appreciable number of the first round of Type 1a supernovas to occur after the Big Bang. If there are enough of these prompt Type 1a supernovas, it may be possible to measure the effects of dark energy on cosmic expansion during earlier times. As we learn more about them, other Type 1a supernovas continue to provide surprises. Chandra's observations of the youngest known, about 110 years old, galactic supernova remnant, G 1.9 plus 0.3, have yielded the first definite detection of radiation from radioactive decay of scandium nuclei, which in turn came from the radioactive decay of titanium. From the strength of the scandium X radiation, it is possible to compute the amount of titanium produced in the explosion, a little more than 7 million times the amount of titanium in Earth's crust, enough to make a fair large number of airplanes, golf clubs, and hip joints. Theoretical analysis of how so much titanium could have been produced seems to require a lopsided explosion, so that the necessary shock waves can propagate faster, heat more, and synthesize more titanium. The spatial distribution of iron and the intermediate mass elements silicon and sulfur suggests that the explosion itself was asymmetric. Incidentally, the estimated amount of iron produced in the explosion is roughly equivalent to the iron in 1 million Earths.